And so there are other ones that can form from this austenite perlite. This is one of the things that makes steel so unique, is these other constituents. And these other constituents form by changing temperature and time, and they can be formed during isothermal holds. Some cases we're gonna go to fairly low temperatures for these, but the two primary ones that we have, which are non-equilibrium phases because they don't appear on the phase diagram, are bainite and martensite. We'll talk about spheroidite as we move forward, but bainite is the way to really think about bainite. It's still diffusion driven. It is really a combination of ferrite and cementite, so it's pretty similar to perlite in a lot of ways, but its properties are significantly different because what it occurs at, and bainite exists at very fine scales, where what we have are very, very small cementite and ferrite lasts. This is less than 1 micron across. And so what we have here that we need to use electron microscopy to even really see bainite. And in some cases, we'll have some martensite around it. But bainite forms as needles or plates, so it's extremely fine. But with that fine scale that it has, it is really extremely strong. And it's something that we're going to take advantage of. So where does bainite fit on these isothermal transformation curves? It was known to form, and since it's called bainite, we know it was named after Edgar Bain, who we talked about developing the concept of isothermal transformation curves, or TTT diagrams. And so bainite's going to form at higher undercoolings below perlite. And so if we think about still this eutectoid steel, we can start at coarse perlite at high temperatures and long times. We come to fine perlite as we reach here. But there reaches a point where, and this dotted line represents that, where we start having enough undercooling that the bainite becomes really the more stable microconstituent. And so after about a certain point, you start to see the fine perlite really start to form this bainite. And with that, since bainite is still diffusion driven, we have the same type of curve, but we see how it becomes more of the C curve coming around. And so with that, we have bainite. And with this, the way to think about it would be as if we start with our 925 degrees C, a completely austenitic structure, and we were to drop to 500 degrees C instantaneously and hold it. So by the time we reach about 1 second, we're going to start forming bainite pretty quickly. And by the time we reach at about 8 seconds, we're at about 50%. And by the time we're at 10 seconds, we are really a completely bainitic structure. So we see just from 625 to 500 degrees C how we go from a fine perlite structure to a bainitic structure in just 125 degrees C difference in temperature. And it's really, the times are almost equivalent to form completely different microstructures, completely different properties with that change. Now, I'm going to skip ahead to spheroidite. And so spheroidite is something you're going to run into, especially if you tend to work a little more in the forging industry or things like that. And spheroidite is a form of perlite, is really the way to think about it. We can say that you can start with a bainitic structure, but you typically don't see that. You typically see a perlitic structure that is really held at a temperature. So you will actually go through, the spheroidite doesn't appear on a TTT diagram. Spheroidite is something you do to a perlite that you've formed from the TTT diagram. And so what it is if you hold a perlitic microstructure at a temperature near the eutectoid, so near that 727 degrees C, for an 18 to 24 hour period, what's going to happen? Well, at that point, what you're going to start doing is you're sort of going through, there's still the driving force a little bit to a point for the volumetric free energy change that we had talked about. But the other driving force that's really going to take hold is the surface energy driving force. And what that's going to do is it's going to convert all of those lamellar perlite structures into spheres. And so we know from our previous discussions that is how you minimize surface energy, is through a spherical shape. And so carbon's going to diffuse. There's no change in composition. There's no change in the amount of ferrite or cementite. but the cementite takes on a spherical shape. And so if you look at this structure compared to the lamellar structures that we see for pearlite, this spheroidite is extremely soft. There's really very little to stop dislocation motion. So plastic deformation becomes fairly easy. And so as I had mentioned, you're going to see this if you work in the forging industry. So what you might want to have, if you need to forge a product, you want to get it to the point where it's rather soft. And if you want to form it, forge it, take a lot of deformation into a part. This is one way to easily do that with a low level of force applied. So spheroidite is rather soft, and just as the name says, spheroidite is the cementite takes on a spherical shape. Now, this takes us into probably the most important of these microconstituents. Bainite's important, spheroidite has its uses, but the one major microconstituent we're going to see is when we rapidly cool, and we call that quenching, and usually quenching is done by taking a material that's in the austenite state at that 930 degrees C and dropping it in cold water. That gives us extremely rapid cooling rates to be able to do that, or gets us to low temperatures very quickly. And so martensite forms when austenite's rapidly cooled or quenched. It's a non-equilibrium structure, but martensite is different because martensite does not occur through a diffusion-based process. It occurs through either stress or strain, and we'll talk a little more about that, but it's more of this shear-based type process when we really think about it. And the way to look at martensite is the FCC is trying to convert to BCC, but there's the stresses involved, and so what it actually forms is not a BCC type crystal structure, but what we consider a BCT crystal structure, this body-centered tetragonal. And part of what drives that is that these carbon atoms, they're in a supersaturated solid solution. So there's more carbon in it than what we would tend to want to expect, because we don't have that cementite forming. So martensite is this microconstituent. It's BCT. I would highlight that is that being a pretty important understanding of what sets martensite apart. But since martensite doesn't involve diffusion, it's represented differently on these isothermal or these TTT diagrams. And so going back to this eutectoid or this 1078 steel, what we tend to see is we have our eutectoid temperature right around 727. We have our coarse pearlite, our fine pearlite, our bainite, and we see that these are all involved in these sort of C-type curves. Martensite is independent of time, and it's only a function of temperature to what the alloy is quenched to. So it's an athermal transformation. And these athermal transformations are represented as horizontal lines on the TTT diagram. And so what we really are interested in is this martensite start and this martensite 90% or this martensite finish temperature. And so we can imagine that if we go from 930 degrees C to 225 degrees C, in this case for this eutectoid steel, instantaneously, we start to form martensite, because this austenite is not transforming to pearlite, it's not transforming to bainite. It's cooled rapidly enough that if we go right to room temperature, we will form a 100% martensitic type structure. And we see how this austenite field will actually increase here. We're going to talk a little bit about how we go through this, because what this allows us to do is start to develop multi-step heat treatment cycles. And so just wanted to give you this. We're going to talk a lot more about this steel. And what you tend to see here is if we change the alloying elements, we can change the shapes of these curves. So this is just a simple plain carbon steel. Now, if you make an alloy steel, we know from our discussion the last time that the two numbers in front tell us that there are some other alloying element additions. In this case, there's the addition of chrome, nickel, and molybdenum. And what these alloying element additions are meant to do, even though there's 0.4 weight% carbon in this steel, by adding these alloying elements, what we do is we're changing the stability of the austenite phase. And with this, we see that by adding these alloying element addition, we get a separate nose for bainite, but look how long it takes to form even proeutectoid, ferrite, and pearlite. This steel was designed to form bainite and martensite. And so we see how the time is switched over. Now, when we develop these alloy steels, The idea is that we make it easier to form martensite because the austenite is stable. If we look here, the martensite start temperature is almost 300 degrees C. And we go back to this eutectoid steel, it's at 225 degrees C. So with that higher martensite start temperature, the longer time that we can hold it at a temperature before we start forming even bainite, it becomes that much easier to form martensite. And that's what the idea behind these alloy steels are. And this is what we're going to call increasing the hardenability. And we'll get into that as we move a little further into the lecture. But with the ability to do that, start thinking in terms of how do you work with larger structures. And so if we take 4340, for example, it's much easier to equilibrate temperatures on a very thin rod versus a very thick bar. Say if you have a 1-inch diameter bar and you heat it up, it gets to temperature a lot more quickly in the middle of it than, say, a 12-inch diameter bar would. What this type of alloying allows us to do is that we can get uniform microstructures throughout, even though we're changing our thermal histories or our thermal cycles. We'll start getting a little more into what's considered the CCT diagram. And what we'll see here is working with this type of structure, as long as we understand the basics of how to read these TTT diagrams, no matter how complex these shapes may get, it allows us to be able to read them pretty quickly.